Okay, this is positive definite matrix day. Our application was the second order equation with a symmetric matrix S. And we solved this equation, second derivative plus S times Y equals 0. And you maybe remember how we solved it. We looked for an exponential solution, e to the I omega t times a vector x. We substituted and we discovered x had to be an eigenvector of S, as usual, and lambda, which was omega squared, is the eigenvalue. But I didn't stop to point out that if we want lambda to be omega squared, we need to know lambda greater or equal to 0. So that is the best of the best matrices, symmetric and positive definite or positive semi-definite, which means the eigenvalues are not only real, they're real for symmetric matrices, they're also positive. Positive definite matrices, automatically symmetric. I'm only talking about symmetric matrices, and positive eigenvalues. Okay, there it is. Positive definite matrix, all the eigenvalues are positive. Positive semi-definite, that word semi allows lambda equals 0. The matrix could be singular, but all the eigenvalues have to be greater or equal to 0. And let me show you exactly where those matrices come from. Those matrices come from A transpose A. If I take any matrix A, could be rectangular, and A transpose A will be square, A transpose A will be symmetric, and it will be at least positive semi-definite. Why is that? This is the simple step that is worth remembering. What's special about A transpose AX equal lambda x? The good idea, multiply both sides by X transpose. Take the inner product of both sides with X. Then I have X transpose times the left side is X transpose times the right side. I'm okay with equation 2. When my S is A transpose A, that's my S. Okay, but now I look at this. That is AX inner product with itself. That's the length of AX squared. Anytime I have Y transpose Y, I'm getting the length of Y squared. Here, Y is AX, so I'm getting the length of AX squared. Over here, Y is X, so I'm getting the length of X squared. And you see that number lambda is, in this equation, I have a number that can't be negative, a number that's positive for sure, because X is not the 0 vector. So lambda is never negative. AX could be the 0 vector. If we were in a singular case, AX could be the 0 vector. In that case, I would only learn lambda equals 0, and I'd be in this semi-definite case. So if I want to move from semi-definite to definite, then I must rule out AX equals 0 there, because that's certainly a possibility. I mean, if I took the 0 matrix, all zeros, as A transpose A would be the 0 matrix. That would be symmetric. All its eigenvalues would be 0. Would it be positive semi-definite? Yes. Yes, all its eigenvalues would actually be 0. Of course, that's not a case that we're really thinking about. More often, we're in this good case where all the eigenvalues are above 0. Okay, so that's the meaning. And now, the next job, how do we recognize a positive definite matrix? It has to be symmetric. That's easy to see. But how can we tell if its eigenvalues are positive? That's not fun, because computing eigenvalues is a big job. But for a large matrix, we take time on that. We didn't know how to do it a little while ago. Now there are good ways to do it, but it's not for paper and pencil and not for eye. So how can we tell that all the eigenvalues are positive? Well, we only want to know their sign. We don't have to know what they are. We don't know we need the number. We just want to know, is it a positive number? And there are several neat tests. Can I show you them? I'm going to have 5 tests, 5 equivalent tests. Any one of these tests is sufficient to make the matrix S positive definite. There is a particular S there that I'll use as a test matrix. So there's a symmetric matrix S, and I know it is positive definite. But how do I know? Okay, well, so 5, can you take 5 things here? They connect all of linear algebra. It's really beautiful that the eigenvalues, that's one chapter of linear algebra. The pivots are another chapter of linear algebra. Do you remember about pivots? That's when you do elimination. So 4 is the first pivot. The first pivot, pivot number 1, is the 4. And then when I take a multiple of that away from that, I get a second pivot, and I'd see that that was positive. So what's that? Maybe I take 1.5 away of this. I multiply that by 1.5, 6, 9, subtract from 6, 10. So I actually get a 1 down there. So pivot number 2 is a 1 in that case, right? 6, 9 taken away from 6, 10 leaves me 0, 1. Okay, it passed the pivot test. Notice I didn't compute the eigenvalues. I'm just doing other tests. Now here's another beautiful test. It involves determinants. Now I have to say upper left determinants. Greater than 0. What do I mean by an upper left determinant? I look at my matrix. That's a 1-by-1 determinant. Certainly positive. That determinant is 4. Here's a 2-by-2 determinant. And that determinant is 4d minus 36. So happened to be 4 again. So the determinant of the matrix is 4. But I also needed the ones on the way. I can't just find the determinant of the whole matrix. That's the last part of this test, but I have to do all the others as I get there. So it passes that test. Check. It works. So that test is passed. I'm doing more work than I need to do because one test would have done the job. Now, here comes another one. S is A transpose A. That's what we looked at a minute ago. If S has this form A transpose A, what did we convince ourselves? We said that this was sure to be semi-definite, and I needed some condition to avoid AX equals 0. There was the possibility of AX equals 0. I'll just bring that down. You remember we started there and ended up here, and if AX was 0, then lambda was 0. We were in the semi-definite case. So I have to avoid that. So I have to say when A has independent columns. And I think I could factor that matrix S into A transpose A. I'm sure I could. And get independent columns, and it would pass test 4. I want to go on to test 5, which is really, in a way, is the definition, the best definition of positive definite. So if I took number 5, it's the energy definition. So can I tell you what that means? I mean that X transpose SX. If I take my matrix S that I'm testing for positive definite, I multiply on the right by any vector x, any x, and on the left by X transpose, well, I get a number. S is a matrix, Sx is a vector, inner product with a vector, I get a number. And that number should be positive for all x. Oh, I have to make one exception. If x is the 0 vector, then of course that answer is 0. All x except the 0 vector. Okay, so that would be a way to, another test. And this is associated in applications with energy, so I call this the energy test, or really the energy definition of positive definite, x transpose Sx. I'd like to apply that test. So you'll see what does it mean. Now we're looking at all x to this particular example. But I won't throw away this board here. You see eigenvalues, pivots, determinants, A transpose A, and energy. Really, all the pieces of linear algebra. The A transpose A, we'll see it more and more. It comes up in least squares. If I have a general matrix A, you know, it's not even square. It doesn't have great properties. But when I compute A transpose A, then I get a symmetric matrix. And now I know also a positive semi-definite, and with a little bit more, positive definite matrix. Okay. By the way, what are there 5 tests for semi-definite matrices? Yes, there are. 5 similar tests. All eigenvalues greater or equal to 0. All pivots greater or equal to 0. I can go down this and just allow that borderline case that brings in semi-definite. I won't do that. Let me take my matrix S, that example, small example matrix, and apply the energy test. Okay. So I'm looking at energy. So I'm looking at x, that's x1, x2, times my matrix 4, 6, 6, 10, times x, x1, x2. That's the energy. That's my x transpose Sx. X transpose Sx. Is that what we wanted to compute? Yes, x transpose Sx. Now, can I compute that? Yes. It's a matrix multiplication, nothing magical here. But when I do, I'll show you the shortcut. When I do that, a 4x1 is going to appear, and it'll be multiplied by that x1 over there. I'll get a 4x1 squared. And then I'll have a 6x2 that's multiplying that x1. So there's a 6x1, x2. And now from this, that was the first component, and now I have 6x1 and 10x2 multiplying x2. Well, that's another 6x1, x2, and the 10 will multiply x2 and x2, x2 squared. I did that quickly. But the result is just easy to see. The 4, 6, 6, 10 show up in the squares. The diagonal 4 and 10 show up in the squares, and the off-diagonal 6, which doubles to 12, shows up in the x1, x2, the cross term. Okay, now why should that, so that's a number for every x1 and x2. Suppose x1 is 1 and x2 is 1, then the number I get is 4 plus 6 plus 6 plus 10. That's probably 26. It's positive. What if x1 is 1? Let me try this. x1 is 1 and x2 is minus 1. Do I still get a positive energy? So my vector is 1 minus 1. So I get 4. Now, because of that, I have minus 6 and 10 from the x2 squared. And that's 14 minus 12. That's 2. It's positive. Well, I tested 2 vectors. I tested the 1, 1 vector and the 1 minus 1 vector. But you have to know that for every vector x, this does turn out to be positive. And I could show you that by something called completing the square. It's not what I plan to do. The beauty is we now understand this energy test, what it means to take X transpose S X, write it out, and ask, is it always positive? Is it always positive? Okay, so that's the number 5 test, but I think of it really as the definition. And it means, can I draw a picture? Here's x1, here's x2, and now this is my function. X transpose AX, my energy. If I graph that, I have an x and a y and a function z, that function of x and y. What kind of a graph does it have? When x1 and x2 are 0, it's there. When x1 and x2 move away from 0, it goes positive. That graph is like that. It's sort of a bowl. And I have a minimum. The main application of derivatives in calculus is to find the test for a minimum and decide minimum or maximum. Minimum or maximum. And you remember the second derivative decides minimum or maximum, positive second derivative, minimum, negative second derivative, maximum. It tells you about the bending of the curve. Well, we're in 2 dimensions now with a function of 2 variables. This is multivariable calculus. So what becomes positive second derivative becomes positive definite matrix, a matrix of second derivatives. This is the whole subject of optimization. Maximizing, minimizing comes here. Okay, that's for another day. I just would like to tell you one more thing about positive definite matrices. I got a book in the mail, which could be quite valuable. It's a little paperback, and the title is Frequently Asked Questions in Interviews for Financial Math. Being a quant, going to Wall Street, becoming rich. So they don't give you all the money right away. They make you show that you know something. And so they ask a few math questions. And the first question was, I was happy to see this. The first question asked, when is this matrix positive definite? Okay, can you see that matrix? 1's on the diagonal. Those are correlation. This is a correlation matrix. That's why it's important in finance. It might be the 3 correlations of bonds and stocks and foreign exchange. So each one is correlated to itself with a full correlation of 1. But there'll be a correlation between bonds and stocks going up together, but not perfectly together, by some number A. And bonds and foreign exchange with some number B, stocks and foreign exchange, some number C. So that's the matrix of correlations. And the key point is, it is positive definite. So if they question, when you go to Wall Street to apply for the money, if you're asked, what's the test on those numbers A, B, C to have a positive definite, a proper correlation matrix, I would suggest the determinant test. The determinant test, if I'm given a small matrix, I'll just do the determinants. So that determinant is 1, no problem. This determinant, what's that 2 by 2 determinant? 1 minus a squared. So 1 minus a squared has to be positive. I'm doing the determinant test. And what's the 3 by 3 determinant? 1 from the diagonal, and I have an ACB and an ACB. I think I have 2 ABCs from the the three terms, now 1 and 2, those terms are have the plus signs. And now I have some with a minus sign, which better not be too big. That's the whole point on positive definite matrices. The off diagonal is not allowed to overrun the diagonal. The diagonal should be the biggest numbers. Okay, so I saw that a squared had to be below 1. But now what's the determinant test? I think this has to be bigger than what I'm getting from this direction, which is a b squared and a c squared and an a squared. Oh, look at that. A squared, b squared, and c squared. That would be the answer. That first test there, second test there. Well, the easy test was just 1 as positive. So really, that's what they're looking for. That would be the test, those numbers. So A, B, C can't be too large, or that would begin to fail. Good. So positive definite matrices have lots of applications. Here was minimum, here was correlation matrices and finance, many, many other places. Let me just bring down the 5 tests: eigenvalues, pivots, determinants, A transpose A, and energy. And I'll stop there. Thank you.